In this section, we're going to explore and define how one determines a proper detection. The sensors inside the all clear are spaced 1.25 inches or 3.2 centimeters apart, which accounts for why the object resolution is approximately 1.5 by 1.5 inches or 3.8 by 3.8 centimeters. Energy is collected in a collimated manner through each collection lens. An object's edge must cross a collection lens to produce contrast and provide a detection. Let's explore contrast a bit further. All clear sensors detect the difference in the millimeter wave energy between that produced by the human body and the edge of the concealed object. This contrast edge is what produces a detection event. The greater the contrast, the higher the probability for detection. Smaller objects are harder to detect than larger objects, as smaller may produce a contrast smaller than the collection lens, as previously illustrated. However, regardless of how small an object is, if a high contrast of millimeter wave source crosses the collection lens, the object has a high probability of detection. There are several key rules for detection that will be covered in this section for both metal and non-metal objects. Let's first start with the metal objects. When considering the detection of concealed metal objects by the millimeter wave sensors, the temperature, color, or thickness of the metal object will not have any effect on the metal object's detection probability by the millimeter wave sensors. Metal objects are also detected using the conventional metal detector coils inside the all clear as well as the millimeter wave sensors. This technology combination enables the unit to offer the full functionality of a conventional metal detector, but with the added ability to detect non-metal objects. Non-metal objects vary in their absorption rate. The absorption of a particular non-metal object is relative to the amount of millimeter wave energy emitted from the body and how much can pass through the object. The greater the millimeter wave absorption, the higher the contrast, which increases detectability. Objects with moderate absorption include items made of plastic, silicone, paper, rubber, and ceramic material. The thicker the object is, the greater the absorption, and therefore the higher the contrast of the concealed object and the probability for detection. Liquid-based objects have the highest level of absorption, meaning millimeter waves are almost completely blocked. Thus, concealed objects such as liquid or gel explosives as small as 1 inch by 1 inch or 2.5 centimeters by 2.5 centimeters can be detected by the all clear due to the high absorption rate. Let's explore thickness in more detail. In simple terms, the thicker the object, the greater the absorption, the more millimeter waves are blocked. The higher the absorption, the more likely detection will occur. Take currency as an example. Currency in large amounts is a concern at border control checkpoints. Large quantities of concealed currency on the body have a high detection rate as the thickness of the currency stack blocks the body's millimeter waves. Small amounts of currency, such as the typical amount carried in one's pocket on a daily basis, can also be detected. It is therefore important that subjects divest prior to being screened. The environment where the scanning occurs plays a vital role in the success of detecting concealed objects. A warmer room yields less detectability than a cooler room. This goes back to the temperature contrast previously discussed. Cold air cools the outside surface of the object, which can make it easier to detect. However, cooled regions on the body may produce edges, resulting in possible false alerts. It is this reason why the all clear is designed for an indoor climate-controlled environment, preferably below approximately 77 degrees Fahrenheit or 25 degrees centigrade. Extremely hot or cold temperatures will also affect performance.